Hey there, this video I'm going to show you how you can write the gradient boosting machine learning algorithm from scratch in the R programming language. This is a very popular algorithm for doing classification and regression. And although there are packages available for doing this within R and other popular programming languages, I think it's interesting to kind of create this algorithm from scratch to really understand how it works. So that said, I have RStudio open right here. I have an empty environment and just a blank file right here. So as I was saying, if you wanted to do gradient boosting in R, the best package to use is called Ggplot. But as I mentioned, we're not going to use that. We're going to try to do things from scratch as much as possible and kind of understand how gradient boosting really works. So that said, we will need some libraries. We're not doing completely from scratch. So one library we will need is tree, which is used for decision trees. So as you'll see as we move on, gradient boosting works by building decision trees off the residuals of previous decision trees. So we will need that, and that can be installed just with, I guess I can show you on a new line, install packages tree. We'll also use caret just to calculate the root mean squared error. And we will use Ggplot 2. I guess that's not essential, just kind of will be interesting to visualize the results later on. And we might also use random forest just to compare the model we build to a random forest, because it's another popular algorithm for machine learning. So if you have those installed, you're ready to go. So we can just run those and make sure we're good. And I already have installed these, so that should work. All right, and for the data that we're going to use, we're just going to use the MT cars. It just comes with base R. So if you're not familiar with that data set, it's about 32 rows, I think. A couple different cars. We have the MPG rating and some different features about our car. It's all numeric values, so it's pretty easy to work with. And yeah, it's pretty small, but still good for demonstrating some concepts. So let's just put empty cars into a data frame. And just thinking ahead a little bit, we're going to be predicting the MPG, miles per gallon. This will be our Y variable. And so all these other variables will be our predictors or X variables. So let's just grab those right now. So names of the data frame from the second column to the end. So I guess we can run that one. So if we look at X vars, awesome. And then this is just looking forward a little bit, but we're going to want to put these all into a list or a big string separated by a plus sign so we can pass it to the model. So this will just save us some time. So if we look at that, if you're familiar with R, you'll see, you'll know why this is going to be useful. All right, so now that we have that, let's just take a look at our data set one more time. So we have this column that we're going to try to predict and these other ones. So I guess I should have mentioned this at the beginning. This video, I'm not going to go too much into exactly how gradient boosting works. This is more of a application example. So there's a lot of good videos out there that will kind of go into the details. One I watched that I really enjoyed was from the channel is called StatQuest. If you look up StatQuest gradient boosting, I'm sure you'll find it. I couldn't write it like that. I think it's called StatQuest. Anyway, so you should have a basic understanding of how gradient boosting works before kind of continuing on. So if you have that, you'll know that we have to have a base prediction. So a common thing to do and something we'll do here we'll say just like our first prediction, we're just going to say the mean of, that MPG column. And we'll just attach that to the data frame. So this is just our prediction. And obviously that's a very bad prediction, just saying no matter what the car is, we're just going to say, I think the miles per gallon is just going to be the average of all the cars in our data set. But we do need a base point to work off of. So let's see, the next step is then to calculate the residuals. So I'm just going to call a resid1, and you should be aware that a residual is just the difference between the actual value and our prediction. So our actual is our MPG column, and subtract our prediction 1. And that also gets saved to the data set. So now if we see, we have our prediction 1 and our residual 1. So this is just 21 minus this is our residual. So this will be different for each column, just depending on that MPG. So that's pretty straightforward. And that's just we can call this like round 1 of gradient boosting. And it's kind of interesting because it's the first round and we're just using this very basic prediction, just taking the average. But now from this point on is where it kind of gets interesting, where we'll start predicting this residual 1 column. So we'll use our X predictors, so cylinder, dispersion, horsepower, all that stuff, or not dispersion, displacement. We'll use these columns to predict this residual. And so prediction 2, our next prediction, is going to be a prediction of this residual, and so on. I guess we'll just hop right into it. So to do that, we need to create a decision tree. So that's what this tree package is doing for us. So this is tree, and our model is going to be MPG, and then all those columns. So we could write this out, but that gets a little annoying. So we're going to do the shortcut where we do something like this, which, to be honest, it is a little difficult to know whether this is actually quicker than typing it all out, because R is a little strange in how they do this. So we're going to predict residual 1, this column right here, based on the content of, or based on these X vars. Then I need a comma there, and we just need to say data is a data frame, close that out. Okay, this should work. Hopefully I didn't miss a comma. Awesome, so we can actually look at that model. Very good. We could look at this closely if we really want to know what's going on, but it doesn't matter too much to us right now. So that is our model. So now we can do our data frame. Our second prediction is going to be the prediction using that model on our data frame. We'll just put that in to that data frame. Awesome, so now we have this first prediction, which is just a mean, the residual of those, and this prediction 2, remember, is the prediction of these residuals right here. So you can see this one's kind of close. Not too good, honestly. They're getting there. So here's the next step, as you might have guessed, is we're going to calculate the residuals of this prediction. So the tricky part to remember is we're not just going to take this actual value plus this residual. We actually need to kind of combine the two predictions. So this is our first prediction. And so our next prediction is actually this one plus this one. And then this one plus this one for each of the other ones. So if we were to do that, I'm not going to run, or I guess I can just run it right here without saving it yet. Let me look at the column names again. So our prediction would be data frame prediction 1 plus the data frame of prediction 2, because this is just our average, and this is a prediction of the difference between the average and the actual. So this should actually be pretty close. Okay, let's run that. So this is a little messy to look at, but so our prediction for our first column was 19. The actual is about 21, 19, 21, okay, makes sense. This one we predicted 22.58 for a 22.8. So that's good, but if you're looking into gradient boosting, you should know that it's actually a little too good. We're gonna overfit the model if we don't introduce something that is called the learning rate, or some people give it different names. But basically, we don't want to use all the information in this prediction to the second prediction. Instead, we want to do something like the first prediction plus some value, some learning rate times this. It's kind of like discounting that value by a little bit. So this is somewhere between like 0.0001 and 1. Let's just stick with 0.1 for now. So in some cases, this actually improved our score, and sometimes it didn't. So for example, this third row used to be 22.58, which is pretty close to the actual. But now, because we're only using about 10% of that prediction 2, it's going to be a little smaller. So this prevents overfitting. And because we're going to do multiple rounds, like I said, this was round 1. What we just did now, or in the process of doing, is round 2. So we'll do a learning rate and then multiple rounds and slowly step towards an accurate prediction. So let's just go up here and define our learning rate. We'll stick with 0.1. We'll just save that right now, why not? Okay, so that means, kind of going back to where we were, if we're going to look at the residual for this prediction, this will be our prediction, which means our residual, maybe I'll just copy that and say the new column residual 2 will be the difference between our actual column, which is the miles per gallon, subtracted by, I'm just pasting that in, this mess. So our first prediction plus, we can now enter this learning rate, times data frame in the second prediction. And I think I forgot a parenthesis. Okay, so that's our residual, because it's the difference between our actual and our prediction, which a prediction is the combination of our first prediction and our second prediction. So let me run that learning rate cell, and now I can run this. And now if we look at that data frame, we have first prediction, first residual, second prediction, and the second residual. And so this is we've already explained the residual, but it's important to remember that this prediction is the prediction of this residual, and our next prediction will be a prediction of this residual. So kind of, if I could draw a line right here, we could show exactly what we were predicting. So as you can kind of imagine, we could copy this again. We could say this was round 2, and this is round 3. So this time we're going to predict our second round residuals, and let's call this residual 3. Okay, and this is where it gets a little messy, because now we have to do, our prediction is the combination of our first prediction, the learning rate times our second prediction, plus the learning rate times this third round prediction. Does that look good? Okay, so let's run that model, make that prediction, and calculate those residuals. Okay, awesome. So that's kind of where we're getting at right now. So if you imagine going for even like a fourth round, this expression right here is going to get pretty messy. And we're repeating a lot of code. So this isn't, even for this example purpose, not the best way to continue. It is a good way to see behind the scenes how things are working. But now that we have a kind of a handle on that, we might want to move to a better approach where we can just do just a for loop for each round. So to set that up a little bit, first let's just define how many rounds we want to do. So let's, for now, just say we're going to do 10 rounds of this. We can keep our learning rate the same. To prevent this expression from growing long each round, what I'm going to do is make a separate column just called prediction. And this prediction column will hold the total prediction for each round. So at round 1, it'll just be this. At round 2, it'll be this combined. Round 3, this, and so on. So we'll just say, let's see, the best way to do this. We can just say, oops. We'll just set this to just nothing for now. And we'll add this on. So df1 will be our MPG column. And then that'll be our prediction, which is just blank for now, and then everything else. Okay, let's just restart here. And look at, okay, sweet. So this will be our actuals, and this is where we'll keep that kind of bundled up prediction as we move through the rounds. So, and then I guess we can move on to round 1 then. So we still want to make prediction 1 equal to that mean. But because it is the best prediction we have so far during round 1, we'll put prediction 1 also into this prediction column. And instead of predicting, I guess it doesn't matter in this first case, but let's get in the habit of just calculating the residual as the actual minus our predicted column. Let's test if that works before moving on. And run that again. Okay, so that looks the same, which is good. So now let's do the for loop. So let's do for I in, we're going to start at 2 because we already did round 1. N rounds, which I don't think I ran yet, so I'm going to run that. So the steps were, I guess right here, we can just kind of move this into the for loop. We'll have to alter it a little bit, but the model will be, so to make this dynamic, we're going to say residual. And so on round 2, we actually want to do the residuals of round 1. So it'll be residual I minus 1. And then get the tilde, x vars. Okay, I think that looks good. And then we need to dynamically make this prediction column. So we're going to do a whole lot more pasting. So paste 0 and prediction and whatever I is. So this will be prediction 2, prediction 3, and so on. And that'll predict, model, data frame. Okay, that looks good. Separate that a little. So now we need to kind of copy this format and put our prediction into that prediction column. So we'll just say df prediction. And so this is, remember, we're just kind of building on top of that. So this prediction column will be what was previously in the prediction plus the learning rate times this newly predicted column. So I'm just going to grab that and double check parentheses and everything. I think I should be good. Yeah, okay. I guess we'll see when we run it. So we can delete that because, actually no, we still want that. Because now we want to save these residuals into a new residual column. So this will be, we'll do RESD, and this will be I. So for round 2, this will be residuals 2. And we don't have to do this messy expression anymore. We'll just do the data frame MPG minus data frame prediction, because we put the prediction into there. So I think that should work fine. Let's delete that and give it a go. So just to be safe, I'm going to just run it from up here. Round 1. Awesome. So nothing broke, which is a good sign, but we can't really look at the progress of anything. So that's why we did bring in this caret library. I just kind of forgot to add it as we just went through. But we're going to use caret to calculate the root mean squared error for each of those models. So probably the best way to do that, we can just calculate this. So RMSE, that belongs to the caret library, like I said. So you just give it, we can look at the little note, give it like predicted and observed, or other way around, doesn't matter too much. So it'll calculate root mean squared error between the miles per gallon and our prediction. So let's see, the best way we can put our results, maybe not the best way necessarily, but the easiest way I can think of, we can keep track of the round. So we know this is going to be the first round, and then the root mean squared error, which will be, we'll just define it as a little vector of that root mean squared error. Let's just double check this works by running everything again. One thing nice about working with a small data set is it's real quick to run everything. Okay, so results. Awesome, sweet. We have round 1 with that root mean squared error. So now we just need to do the same thing. I guess not exactly the same. We don't need to create a data frame each time. But we do need to calculate the root mean squared error. So let's do that down here. So that's a nice thing about putting our prediction in one column. It's the same call. And we're just going to rbind, just bind a row onto the data frame. And just so those match up, we'll just use a list. So round, this will equal ri, that counter. And then RMSE equal this root mean squared error right here. All right, let's run it one more time. I guess I can start from right here. Okay, so let's look at our results. Sweet, so this is what we were hoping to see. As the rounds continue to progress, our root mean squared error goes down. So if you understand even just the basics of root mean squared error, or just the word error alone, you would imagine that we want our error to go down within our model, which it is. So that's good news. So that's obviously not a very comprehensive, or a, comprehensive, it's not a very like ideal way to implement gradient boosting, because we don't really have a model object that we can apply to future data sets. And like I said, if you're using a real package like random forest or tree, for those respective ones, for gradient boosting, it's Ggplot is, I think, the main one people use if you wanted to get serious about stuff. But just for this sake of understanding, it's kind of interesting to see that we can actually create a gradient boosting process from scratch like this. So just for fun, we can actually compare these results to kind of like a baseline to just some other algorithms. So I'm going to grab this code up. Where to go? Yeah, right here. So let's just compare to other models. So we'll call this just our basic tree model. And so we're already using a tree, but instead of predicting a residual, we're just going to predict miles per gallon based on those X variables. Sweet. Can I grab those? No, I'll just write it. So the prediction will be the model. Oops. And then the tree root mean squared error will be what we've already seen. I'm going to copy this. Like I said, we brought in the random forest. They're very, I mean, random forest and gradient boosting are pretty different in their approaches, but they both kind of are built off just a basic decision tree algorithm. So I thought I might as well bring it in to compare. So let's run those and then run that. So we did bring in this Ggplot library to make a visualization of these scores, and might as well use that. I'm going to make my little plot window a little bigger. And so let's make the Ggplot. We'll make a line for those results. We'll put round on the bottom, root mean squared error, oops, backwards, on the y-axis. Okay, let's just run this first. Okay, so this is what we expected. And we already looked at the data right here. It just goes down over time. So that's very good. Let's check out the score for those other ones. So we'll use H-line, which is just a horizontal line. Give that a y-intercept. This will be our tree, root mean squared error. And let's just give it a different color so we can differentiate. And I think you can also give it a line type. Okay, while we're at it, let's add that other one. We'll add the random forest and blue. Okay, let's run all these. All right, so that's, I'm going to take one out because that's a little tough to see what's going on, that blue line. Oh, got rid of that plus that was going on. Sorry about that. I must have made a mistake here somewhere. Let's clear those. Okay, so that graph's working right. All right, so that red line's way up here. So that's suggesting that the tree root mean squared error is way up there, which doesn't sound right to me, to be honest. I mean, it's correctly coming through. Oh, I see. Sorry about that. This tree model should have been right here. And same with this RF model, should have been right there. That's what happens when you copy and paste stuff. Okay, so let's run those again. Get accurate predictions now. We can uncomment that one. Okay, this should be a little better. Let's clear this plot just in case it gives us an issue again. Oops. Okay, so this is something I was expecting to see more than that issue from before. So it looks like at round 10, the root mean squared error for our gradient boosting was about 2.75, somewhere in between there. Let's see who's red. The tree model was a little below 2, and the random forest was a little above 1. So based on that alone, you might think, well, I guess our gradient boosting model didn't do too well. But that's the nice thing about our little implementation is we can easily change some of these factors. So let's just bump up the rounds to 20. And we do have to run all these again real quick. So I'm just going to fly through this. Okay, look at that. So with that 20 rounds, our model is now, our final model right here is doing better than that just a simple decision tree. Still not as good as the random forest. So let's mess with it a little more. I'm going to do 30 rounds and learning rate of 15%. So run through again real quick. All right, so now we're below, performing better than the random forest model and the basic decision tree model. So, I mean, I've said this a couple times already. This isn't a very realistic example. We have the luxury of messing around with these parameters, but we're not messing around with any of the parameters in this random forest model or decision tree model. This isn't necessarily to say the gradient boosting is always better, because that's never the case with any machine learning algorithm. And we are only looking at error rates within a training set. We don't have a validation set to kind of test these models on, just the way we implement on our model. But it is interesting to see that, see this curve as it goes down. Just by predicting those residuals time and time again, you actually get a very predictive, very accurate model, which is pretty interesting. And like I said, gradient boosting is pretty popular out there, so thought it'd be cool to kind of see exactly how it works. And let's see, it's only about this much code we had to do. The rest of it was kind of just bringing stuff together. And obviously we didn't have to write the tree from scratch. That was already provided for us. But even then, it's pretty simple to implement. So thanks for watching.